Up next, we have something that could shape the future of technology: cryptography deep tech. Join us as we explore the practical opportunities within the world of cryptography led by the experts in the field. Our second panel includes Professor Shweta Agrawal from IIT Madras, Dr. Nishanth Chandran from Microsoft Research India, and Professor Chaya Ganesh from IISc. They will shed light on the future of cryptography. So to steer this insightful discussion, please join me in welcoming Professor Manoj Prabhakaran from the CSE Department, IIT Bombay, who is also the Principal Investigator of IIT Bombay Trust Lab. We request Professor Manoj and the panelists to join us on stage. So Professor Manoj is the Vijay and Sitavashi Chair Professor in the Department of Computer Science and Engineering at IIT Bombay. He is a recipient of multiple prestigious fellowships and awards. He serves on several editorial boards and committees like the Journal of Cryptology, Theory of Cryptography, and many more. His research interests include theoretical and applied cryptography, topics in information security, topics in theoretical computer science.
So it's my great pleasure to introduce my esteemed panelists. I'll briefly introduce you to them. Professor Shweta Agrawal from IIT Madras. She's an associate professor and a Venki Harinarayanan and Anand Rajaraman faculty fellow at the Computer Science and Engineering Department at IIT Madras. Her research interests are in cryptography, information security, and generally theoretical computer science. She earned her PhD from the University of Texas at Austin, and during her PhD, she also worked with Dan Burney, who happens to be one of our advisory board members at Stanford, and Professor Sriram Vishwanath in the field of information theory. She spent 2 years as a postdoc at UCLA with Professor Amit Sahai, and she has several accolades to her name, which I will skip for sake of time. Nishanth at Microsoft Research India. Nishanth Chandran is a principal researcher at MSR India. His research interests are in problems related to cryptography, cloud security, confidential computing, and secure computation. Prior to joining MSR, Nishanth was a researcher at AT&T Labs, and before that he was a postdoctoral researcher at MSR Redmond. Nishanth has received several accolades and has several papers at top venues, both theoretical venues and applied venues, so StockFox and so forth, as well as IEEE security and privacy, other such venues. And also he has interest in quantum computing, quantum cryptography, I should say. His position-based cryptography paper was selected as one of the works invited to QIP 2011 as a plenary talk. He received his PhD from UCLA and a BE from Anna University, Chennai. And he also happens to be an All India Radio A-grade musician. He plays violin. He's a professional violinist. We should have had you, do a little bit of that at the Trust Summit here. Unfortunately, we didn't have enough time. And he has played with in international venues such as the Hollywood Bowl in LA and the Madras Music Academy, Chennai. Chaya Ganesh is an assistant professor in the Department of Computer Science and Automation at IISc, Bangalore. Before joining IISc, she was a postdoctoral researcher in Aarhus University, and prior to that, she received a PhD from NYU Kuran Institute of Mathematical Sciences. Her research interests are broadly in cryptography and security. More recently, she is exploring efficient zero-knowledge proofs and rational cryptography. She has won the IBM Global University Award, Google and Protocol Labs research grants, Infosys Young Investigator Award, and Intel Rising Star Award. And she served as the program co-chair of the Theory and Practice of Blockchain Workshop and helps co-organize Bangalore Crypto Day. Okay, so thanks everyone for joining. The plan for this panel is to introduce you to a few very prominent topics in theoretical cryptography which may not have received as much attention in the industry or in practice. And I want to ask our experts here about the areas they work in and how they might be part of industry going forward. So let me start with Nishanth on the topic of secure multi-party computation, which is something that's been working on for a long time. And maybe, Nishanth, you could tell us a little bit about what this technology is, some use cases.
Thanks, Manoj, for having us over here. It's great to be here. So yeah, I work in the area of secure multi-party computation and been working on that for a while now at Microsoft Research. Secure multi-party computation is at a very, very high level. If you have multiple entities who are bringing in private data and they don't trust each other or any entity, but they want to run some computations on this data, right? Can they actually do this without having to give their clear text data to anybody? And amazingly, it's been known for about 40 years in the theoretical cryptography community that this is indeed possible for any kind of function that you want to. But over the last maybe 5 to 10 years, there's been an explosion in how practical this technology has become. I'll give you some examples of the types of use case scenarios where it could be useful. Let's say I'm a bank and a customer comes to me and I want to check if this customer happens to be on some fraud list or just a list that I want to query, right? And this list is being maintained by some other entity. Maybe it's maintained by a law enforcement agency, or maybe even maintained by a competitor bank, right? And now I don't want to reveal my query to the other entity because that customer has come to me. I don't want to tell them who are my customers or potential customers and so on. At the same time, the list itself cannot be made public because that's confidential information. And so can we actually query this list in a privacy preserving manner and just get a yes or no answer? I just want to know whether this customer is present on a blacklist or a white list or something like that. You can envision other kinds of scenarios as well. And I don't want to learn anything else about the database. At the same time, the owner of the database should not learn anything about the query that's being made, right? And cryptography makes this possible, and it's very practical to make these kinds of queries possible. Another type of use cases which Satya also spoke about briefly in the previous panel is in the context of machine learning, where let's say I have developed a machine learning model based on data that I have collected. I might be a hospital. I've seen a lot of patient data, that patients that have come to my hospital. I've trained a machine learning model for whatever it might be, disease diagnosis, prediction, and so on. And I want to offer this as a service to other hospitals. But that hospital is getting patient information, and that hospital does not want to reveal their patient information to me in order to be able to execute this machine learning model. I don't want to reveal my machine learning model to the hospital where I'm actually offering this as a service, because that's my intellectual property, because I got a lot of these patients and I was able to train this model, right? So how can I offer inferencing as a service to other entities without revealing my intellectual property, but at the same time I don't get to see what it was actually queried on, right? So there are these two entities that are bringing in private information, and I want to derive some utility out of both these entities that are, both the data that's coming from these multiple sources. You could also think about like machine learning training algorithms, multiple entities bringing in private data, and you want to be able to run a machine learning training pipeline through this entire workload as if you had access to all of the data in one place, but actually you don't have. And then also, we've also been looking at use cases like fraud prevention, like you want to do banking fraud prevention. Today, banks get a lot of signals about the customer when they're trying to log in or make a banking transaction. Things like what device are you using, where are you using it from, and so on and so forth. But that information is siloed within the bank. And if you could get access to information from other entities, for example, if you could get access to information from telecom service providers that know a lot about actually the customer. They know a lot about your mobile phone, your normal usage patterns, your normal locations, and so on. This could actually go a long way into mitigating lots of fraud that takes place, particularly through social engineering attacks. Those kinds of things could actually be mitigated if this information could be shared. But there are privacy risks here. The telecom service providers don't want to reveal or cannot reveal the locations of their customers and so on. and banks also don't want to do the same, but you're just interested in something very specific, like you want to run some algorithm to check if this could potentially be fraudulent and so on, and secure multi-party computation could help there. So a lot of our work has focused on how to make this technology more practical, more usable, and scalable to real-world use cases.
Okay, thanks, Nishanth. I'll come back to all the panelists about more of this, but let me move on to Chaya on a related technology, and that's zero-knowledge proof, something we already heard a bit about. But of late, it has become much more practical and of interest due to its relevance to blockchains, in particular the non-interactive version of zero-knowledge proofs. So Chaya is an expert working in this area, and could you please tell us more about what zero-knowledge proofs are and how they're useful?
Sure. Thank you for having me here. I'm very happy to be here. Zero-knowledge proofs are a very high level, it's this primitive that allows an entity called a prover to prove that a certain claimed output of the computation is the correct output to a verifier without revealing any of the secrets involved in the computation. If I may interpret your question more broadly and talk about just proof systems instead of just zero-knowledge proofs, because there are other properties of a proof system like succinctness that is interesting even when we don't care about zero-knowledge. So proof systems allow us to convince a verifier that a computation has been done correctly when either the verifier is a light client, so it cannot perform the computation, and verification is much, much cheaper than the computation itself, or the verifier cannot perform the computation because we don't want to reveal the inputs to the computation and we want to prove. So proof systems have this zero-knowledge property that gives us privacy and succinctness property that gives us scalability, which is important in applications I'll talk about. So a couple of use cases to illustrate the power of proof systems. About the zero-knowledge property itself, one example is in proving compliance with a predicate without revealing our secrets. For example, we can think about network middle boxes which check that client traffic is conforming to some network usage policies. So one could imagine being able to do this in a privacy-preserving way, like a zero-knowledge middle box where we encrypt all the traffic, but now use zero-knowledge proofs to show that the values underlying these ciphertexts are actually complying with any usage policies we might have. Nishanth already talked about privacy-preserving ML using MPC. Zero-knowledge is another solution that you could use to prove a variety of interesting things in the ML pipeline. For example, one could ask that, Nishanth also said that these trained ML models are sort of proprietary. So people might not want to reveal these model parameters. Given that today we use all these ML models to make decisions that are sort of societally important, there are questions about fairness. So one could ask, can we have these ML owners prove that these black box models, which they don't want to reveal in the plane, satisfy some well-defined fairness criteria, right? This could be any definition of fairness that is an orthogonal problem, but if we do have a definition of fairness, something like, if I change the protected attribute, accuracy doesn't change too much. If that is my fairness definition, you could use a zero-knowledge proof to prove that this hidden ML model satisfies this fairness definition. One could also answer integrity questions that Satya talked about in the previous panel, where we might want to prove that a certain ML model has actually been trained on some secret but authenticated data. Like a trusted party has signed all this data, we don't want to reveal it, but we want the guarantee that this ML model I'm using actually comes from using a given training algorithm on this secret and signed data. But we could think about more problems in the entire ML pipeline where zero-knowledge proofs are a very powerful tool to do it. I just want to give one more example where succinctness is the crucial property that gives us the desired property in an application. This is the ZK rollup application. It's called ZK rollup, but really it's not about zero knowledge, it's more about succinctness. So if we imagine in a blockchain setting, there are transactions that are coming in, and every transaction sort of updates the state to reflect how the transaction changed the state. Here we don't want every verifier in the system to re-perform this computation in order to come to the same state. So one could imagine running a batch of transactions and give a proof of computational integrity that all of these transactions have been executed correctly and the final state is the updated state after applying all of these transactions. So this is enabled by the succinctness property of the proof system, where the proof itself is small and verifying the proof is much, much cheaper than performing the computation itself. So one could imagine a bunch of use cases where either we want the property that we cannot perform the computation on our own because there are private values, or in a blockchain setting where things are public, there's a public chain, there's a public update, but we don't want everybody in the network to perform computation that sort of grows with the length of the chain. So here, a succinct proof system could help us.
Thanks, Chaya. So let me turn to Shweta. So Shweta, you work on a couple of, work on several things, of course, and I want to ask you about a couple of things relevant to the panel here. One is, we've been talking about post-quantum secure cryptography, and that's kind of a very real and practical question nowadays. And some of the cryptographic tools underlying that, things like lattice-based cryptography are things you work on, as well as you use them for some of the fancy, futuristic cryptography, right? Like functional encryption. So could you tell us a little bit about both of these applications?
Sure. Is it working? Okay. Yeah, so first of all, thanks for the invitation. It's a pleasure to be here. So post-quantum cryptography, we've already heard about. Shikhar also talked about it. So everybody knows that, you want algorithms to be resistant to quantum computing. And we have several candidates out there. Lattice-based cryptography is one of the leading ones. So in particular, like in the NIST standardization process for post-quantum cryptography, 3 out of the 4 final chosen algorithms were lattice-based. So lattice-based cryptography gives you post-quantum crypto, which is considered very important. And the mathematical structure of lattices is such that it actually gives you a whole horde of applications that are very interesting, even if you're not zoned in on post-quantum cryptography. So even if you were just to think about what are novel things that you could do in cryptography, the best example of this is fully homomorphic encryption, which also we've heard a little bit about. Fully homomorphic encryption allows you to compute blindfolded, so to speak. So if you have encrypted data and you want to run a machine learning algorithm on it, in theory, fully homomorphic encryption makes this possible, and this is also something that you can get from lattices. I'll also touch upon the other application Manoj asked about, which is that of functional encryption. This is something I have worked very extensively on. So functional encryption is the idea that you want to run computation on encrypted data, but you want the output of the computation in the clear. Now note the difference from fully homomorphic encryption. In fully homomorphic encryption, what happens is that you have data. So all of us in this room, right? All of us have our private data, which is encrypted. FHE, fully homomorphic encryption is abbreviated as FHE. This is going to let us do a computation and obtain an output which is nevertheless still encrypted. So you can't learn the output without the secret key. If you have the secret key, you can learn not just the output but also the input. So this is something which is giving you a very nice expressive power in terms of computation, but actually in terms of security, it's a little bit problematic if well, it depends on the application. So if you give the data, encrypted data to a server and the server computes something, gives it back to you. So you have the secret key, you can open either the output or the input. In such a scenario, it's fine. But it's not fine if you want somebody else to open the output, right? So if the data is mine, so let's take an example. So genomic data, okay? So let's think of personalized medicine. I like to use this example because I think it really reflects the tension between functionality and privacy in a very nice way. Everybody agrees that medical research is important, and if everybody's genomic data was available, then you could do studies that try to find correlations between DNA patterns and disease, for example, right? But now genomic data is obviously super private. Nobody wants to share it or use it for computation in untrusted environments. So if all of us were to pull together our genomic data, this could help with medical research. The problem, of course, is, who gets to read the input and who gets to read the output. Most of us are going to be fine if it's only reading the output, but nobody is going to be fine if it lets you read the input. So this is a scenario in which FHE or homomorphic encryption is not really giving you a solution, right? Because whoever can read the output can also read the input. So this is a problem. In something like functional encryption, you're going a step further. So functional encryption is more powerful than homomorphic encryption. It allows you to give sort of restricted keys, which allow the key holder to only open the output but not the input. Okay? So it's something that is more powerful. And these are all things that can be built from lattices in the context of functional encryption. This is not a blanket statement because there are various parameters of interest in these schemes, and there are some things you can you can build from lattices, some things that you cannot, and so on. But lattices do enable a lot of new functionality that other mathematical assumptions don't.
Thanks, Shweta. I hope our panelists didn't load you with too much information. These are all somewhat seemingly similar sounding cryptographic tools, but with very different use cases. In a way, you could think of everything as instance of secure multi-party computation. Data is sitting with many people and you're computing on it. But zero knowledge proofs are a certain kind of computation, and when they're non-interactive, that's the power they're bringing in often. And functional encryption, again, it's about not everybody being present at the same time. You can do certain things offline. So, of course, if you are interested in getting into the more details, welcome to talk to our panelist offline, or we can provide more resources. But I hope it gives you a sense of there is a lot of cryptographic magic that is possible. But some of this is kind of theoretical, some of this is more practical than the others. And it's not often very obvious, which ones are practical practical at the moment, and which ones will probably take longer to be practical. I guess even, as cryptographers, it's not very easy for us to know at any given time what is very practical. So I'd like you all to kind of take on that question and tell us, how much of this has already become practical, and what are the bottlenecks in making more of these technologies practical. So if you were to have a startup based on some of these technologies, what are the challenges they face and what are the opportunities they have?
Okay, I'll go first on the multi-party computation or MPC front. So I think, as I said, over the last 5-7 years, there's just been dramatic improvements in the performance of multi-party computation protocols. And almost any scenario that you can think of today, performance I don't think is the bottleneck as such. We have drastically brought down, just these lookups that I was talking about, querying a private database or running machine learning workloads. Today we can take the latest and greatest large language models also and run them also through machine learning, through cryptographic pipelines, and you can actually get secure computation protocols for all of those. And the overheads are not much, like things that are completely acceptable for many of the real world use cases that we are looking at. I think some of the issues that might be there is that a lot of these protocols are very, very dependent on the use case that you're looking at. So you need to look at the use case and say, okay, this is the protocol that I need to come up with, and that would be the most efficient. General solutions exist, but if I were to take complete generic solutions and apply them, then I would be stuck with humongous overheads. Within domains, you have general solutions. For example, within the machine learning context, you may have like specific solutions that work well within the machine learning context, but the kinds of solutions that are required for machine learning are very different from the kinds of solutions that are required for looking up into a database or doing, location proximity matching and so on and so forth, right? So that I think is a challenge that startups and so on would have to go after one particular use case. And we have seen this even in the history of startups, in the short history of startups in MPC throughout the world as well, right? People have started with trying to build a very, very generic framework to solve multi-party computation for arbitrary computations, and then they've narrowed down on one particular use case and said, this is what we'll nail down. And perhaps the biggest example is unbound technology, right? Which started with a lot of MPCM, because in theory you could do anything you wanted to, and then went after distributed signing, right? And then how do we do threshold signing, and went after that and nailed that use case, and then was acquired by Coinbase and so on. And you can see that even in the NIST standardization, right? That NIST is also going after like threshold cryptography and saying, let's maybe take that use case and standardize that. So I think the applications might drive the adoption of the technologies.
And just to kind of follow up on that, on ML side, Satya was mentioning, inference is now feasible for many problems, but training is a big challenge, right? Do you think even
training also can be done? I think there are other challenges in the training context that are not present in the inference context. Things like what do the machine learning models themselves leak? Can they say something about my data and so on? And then the overheads are such that, I mean, for inference, if I had an overhead of 3 to 4x, it's totally acceptable, because if something was taking 10 milliseconds in the clear text world, if it took like 30 milliseconds or 40 milliseconds in cryptographic world, it's totally fine. Training workloads are so complex today that they are taking like 10 weeks to train a model in clear text, right? And so then if I say, okay, it's going to take you a year to train that model because of the overheads that we brought in, that's not going to be acceptable. Yeah. And so, although the ratio remains the same, yeah, just the scale is problematic.
All right, yeah, thanks. Chaya.
So a lot of what Nishanth said is true beyond MPC as well, that if you have a very specific application, generic solutions are not efficient, but you can sort of specialize and construct very specific zero-knowledge proofs for that statement that's going to be very efficient, right? For example, we can think about anonymous credential schemes where we construct specific zero-knowledge proofs to prove knowledge of signature on a hidden message. These are not generic zero-knowledge proofs, but very specific to these kind of statements, and they're quite efficient. Similarly, we have privacy-preserving proofs of solvency. I guess when Mt. Gox lost a lot of client money several years ago, people started thinking about this problem, and now they are very efficient. There are very efficient zero-knowledge proofs, especially to prove that exchanges are solvent without revealing, what accounts they hold, without revealing their customer balances, and so on. So I guess the bottlenecks in deployment is probably in concrete efficiency. Asymptotically, snarks give sort of the best we can, but maybe concretely there is still some overhead. But another bottleneck that comes to my mind is the gap in protocol specification and implementation of the protocol. So what happened with Zcash a couple of years ago is there was a bug in the Zk snark that was deployed in Zcash. It was not a bug in the sense that there were just some extra elements in the setup, but these extra elements allowed a prover to prove false statements, which in the Zcash setting means that you can sort of print money at will, right? Because soundness is broken, and this is fatal. More recently, an academic paper underspecified how to go from the interactive setting to non-interactive setting. This is called the Fiat-Shamir transform, which is sort of standard in the academic cryptographic community. So we don't always specify the details, but turns out the details are so important that if you miss one input to the hash function in applying your Fiat-Shamir transform, your proofs are actually malleable. You can take a proof that is out there on the blockchain and maul it to become the proof of a false statement. And this is also something that went into many implementations of proof systems. So I think a lack of formal verification of software that comes from cryptographic protocols is probably also something that is a deterrent in more widespread deployment. And the third bottleneck could be, especially in the blockchain setting, is sort of this conflict between regulation and all or nothing privacy. Clearly, in pragmatic settings, there is need for regulatory oversight, and we have to be aware of what the policy is to not throw a generic zero-knowledge proof to make everything private and anonymous, which may not be acceptable to policymakers and law enforcement. But this is something that can be solved with dialogue, I hope, and yeah, we should see more deployment soon.
Thanks. Shweta, you want to?
Yeah, so with lattice-based cryptography, I think that the basic primitives, which is, encryption and signatures, these, of course, because of the NIST competition, they've received a huge amount of attention, and now we have some very good candidates which can be deployed. The NIST competition is also, as already mentioned by other panelists, looking at specific applications like threshold signatures and so on going forward. So these are also applications in which I think we'll see a lot of improvements. Although I have to say that a lot of the practical things that you want, right, like threshold cryptography is one of them. Another one is, for instance, blind signatures. This is something that's used a lot in e-voting protocols, for example. A lot of these practical things which you actually want to use in a quantum safe manner, we don't even have the best theoretical constructions for them. I mean, even asymptotically, they are not super efficient. So what to say of concrete efficiency, right? So, and this actually just has to do with the mathematical structure of lattices as compared to something like groups, for instance. So this is a challenge. Regarding other practically relevant applications, I think with fully homomorphic encryption, again, there has been a huge amount of interest and a lot of effort. Again, it's very application specific, so that's no surprise. If you want something practical, it needs to be application specific. With functional encryption, actually, I think that the space is completely wide open. For very limited classes of functions, there are somewhat efficient theoretical constructions, but I think there is a genuine possibility of using, for instance, multi-input, something called multi-input functional encryption, which allows you to compute on inputs provided by different people. There is a genuine possibility of using that in meaningful applications. The space is completely wide open. So I think in functional encryption, we haven't really crossed the bridge at all from theory to practice.
And just to continue on that, there are also even further futuristic things like obfuscation in the horizon. Right?
Yes.
Which, by the way, is there are a lot of heuristics people use for obfuscation, and maybe the way to get some interest in obfuscation might be to break the heuristics, and then, not that I'm getting interest in the theoretically secure obfuscation is going to help, because theoretically secure obfuscation is still not very practical. I'm just saying that maybe as theoreticians working in obfuscation, we might also want to consider why some of the practical heuristics are not, if you want to get the industry to be interested, why they are not secure.
They are actually. So as of now, I think that the community of theoretical cryptography probably just got a little tired because it was a very long cycle.
I meant to say the heuristics in the practice, the core obfuscation.
Oh, those ones. I see. Yeah. Sorry, I was referring to heuristic cryptographic constructions.
Yeah.
Which
in between, right?
exist, and currently those still stand. So after a very long line of makes and breaks in that space, there exist constructions, heuristic constructions of obfuscation that the community does not know how to break, so we can conjecture that these are secure. But you're talking of what are the obfuscation which is actually used
the heuristic, the ones in theory are still very impractical, the heuristic ones, right?
So the joke here is that, all academics know that obfuscation in practice is very easy. Just have your students code up the problem. That's already obfuscated. So very, very hard to reverse engineer.
Right. And one thing that came up, maybe I'll finish with that, quick comments from all of you on that, is the theoretical papers are written for a different audience. They're underspecified. Sometimes they're vague to an outside reader or even to people in the community, because the focus is on the high-level ideas and not on some of the low-level details, which are considered implementation specific. But to bridge that thing, to go from papers, the cryptography in papers to say a startup's code, right? Seems like we need a generation of people well trained in both programming who also have interest in programming and also trained in cryptography, right? Any comments on that? You can.
Since I have the mic, maybe I'll start. I
Sure.
completely agree. You do need people who are well trained both in cryptography as well as in coding, and this is a really big gap that we have, at least in India. So my colleagues and I at IIT Madras, we have been for a long time trying to build exactly this, that we provide the expertise in cryptography. You don't need to understand how the proofs work, but you need to understand how the constructions work in a way that is deep enough for you to implement it correctly, right? And not leave any holes around the place. But at the moment, at least, we find it pretty challenging to find people who sort of sit in this niche. So indeed, that's something that would help a lot if we had.
And at Microsoft Research, you have had some success in bridging that gap. So maybe you could.
Yeah, I think some of the success I attribute to the fact that the researchers working in various domains got together. Right? So we have people working with us who work on cryptography, on programming languages, on acceleration through GPUs and so on. So we have the multi-party computation project at Microsoft has researchers working on all these aspects. And so we bring in students or interns who have expertise in these various areas as well. And so if you look at crypto implementation, I mean, I may understand some crypto aspects of it, but I may not understand why something is not performant from some other aspect of it. And a programming language person might be able to help with that, or helping us build an end-to-end pipeline. Or most recently, we had some success in taking some MPC protocols and porting them to GPUs and accelerating them. I may not understand fully what are the bottlenecks over there. And we actually had to go back and design some of the crypto protocols, again, keeping some of these overheads in mind, which we did not think were overheads to begin with, because that's not something traditionally you would think as overheads or the most important overheads in the cryptographic world. So I think if that collaboration happens, then students also, you don't need to, it's very hard to get one person who can do everything, right? Same with researchers, same with students as well. But then if you get like more students working on various aspects, but have them interact with each other, I think they can learn from and build this team that actually can.
Okay, thanks. And maybe going to Chaya, another model that might have worked is to lure cryptographers with a lot of money, like that happened in blockchain world, right? A lot of the theoreticians, Jens Groth and who are, right? They built their own startups for their knowledge. We could tell us a little bit about how it worked in that space.
Sure. So Nishanth and Shweta already said that we need people who are interested both in programming and crypto. But I think we also need people who can do formal verification of complete systems, right? Because some of the bugs we've seen in the recent past is not just from underspecified protocols, it's also from incorrect proofs of security and missing proofs of security. Because people come up with a protocol, proof security, and especially in the zero knowledge space where there is so much progress, people optimize and then just argue informally that this optimization did not break the proof of security. And this is exactly where bugs creep in. Like Nishanth said, one person cannot do everything, so I think we really need to work closely, cryptographers need to work closely with people in the formal verification community to sort of build proofs of complete systems.
Okay, thanks a lot. Since I'll take one or two questions from the audience, very quick questions if there are. Yeah.
Yeah, regarding these lattices, I wanted to ask, when one says post-quantum secure, usually one refers to Gauss algorithm, solution discrete laws, etc. For lattices, is it exactly the incompleteness of SVP, or what are the basic issues about why lattices give quantum secure?
Okay, so first I'll repeat the question. the question is about why do we conjecture post-quantum security with lattices, right? Essentially. And I was thanking the speaker for asking the question because it has a really cool answer. The answer is that lattices, the hard problems on lattices, like the shortest vector problem. So first let me make sure everyone in the audience knows what's a lattice. A lattice is basically a periodic arrangement of points. Okay, so just think of a grid. And lattices occur everywhere in nature in 2-3 dimensions. But mathematically, of course, you can think of a lattice of hundreds of dimensions. And then what you can ask is, how do I find a short vector in this lattice? So every lattice has the point 0, okay? And from the point 0, I can draw vectors to neighboring points. And the question is, how can I find the shortest non-zero vector, or which point is closest to the origin in this lattice? So this is a problem. And well, obviously you could just go one by one. So if your lattice dimension is n, this will take 2 to the n time. And this turns out to be effectively the best that we can do. And why don't quantum computers help? The reason, first of all, 2 answers. First of all, we don't know that quantum computers don't help. We conjecture this. Actually, if you ask me, they should help, but we don't know how to make it work. So we are only conjecturing post-quantum security. The second answer is that the hard problems on lattices are geometric problems, and this is a very beautiful thing. So quantum computers, I mean, if you study quantum computing, really the one superpower that quantum algorithms have as compared to classical randomized algorithms is what's called as this quantum Fourier transform. So there is, if you've not heard of it, don't worry about it, but basically there's an efficient way to compute something known as a quantum Fourier transform, and if you have the ability to compute this, then it turns out that certain periodic problems become easy to solve, and that is where all our favorite problems sort of got failed, unfortunately or fortunately. But with lattices, the problems are geometric. And this quantum Fourier transform, we don't really know how to use it with, solving geometric problems. I think that it's actually something that we just don't understand enough. So we don't really know. I think that we might see a quantum algorithm for some lattice problems at some point, but it's very hard to tell because we don't understand. And I mean, I think I'm also maybe giving hope or fear that these things will be broken. It's not the case. We genuinely don't know. There has been a lot of study of cryptanalysis of lattice problems, and we haven't made progress. So, so far as we know, to the best of our knowledge, it should be fine. But yeah, we don't know. But we also don't know if P is NP or not. So I mean, we know very little in general. So this is just amongst that.
And maybe to add to that, we also don't know if the classic or the standard cryptography today can be broken classically.
Absolutely, yeah. So for all you know, I mean, factoring could be broken even classically, right? Lattices could be broken classically. So this is just one of the, I don't know, very uncomfortable land where cryptographers live, right? Never a dull moment and no good sleep ever. So.
Okay. Any other quick question? Last question, yeah.
Like voting systems for the country, for example, or feedbacks, like how do I know that what people really want in such a way that I don't want to know a person's feedback, but collective feedback at a country level. Is it the same problem or it's totally different? So research-wise, is it the same problem or different problem?
Great question. Thanks for asking it. So there are multiple aspects that you touched upon over here. Multi-party computation itself deals with the act of securing the computation itself. We are all bringing in data. We don't want to bring data to a single place in a clear text manner, but we want to get the results of that computation, right? Now, as I think Satya or someone or Sachin spoke about in the previous panel, you may also be concerned about what the outputs of this function reveal itself, right? That is something that's handled by the notion of differential privacy. Right? You can combine the two, and that's what would, if you really want to get a full-blown solution. But these are the two aspects to it. Multi-party computation can enable you to do multiple entities coming in, bringing in their data, and you can compute. So in whatever scenario that you're talking about as well, for voting, it can be used. It's not the most. Voting has, just like how zero-knowledge proofs have, it can be viewed as an instantiation of multi-party computation, but it has its own set of properties that you would like it to have for practical use cases. Voting has its own laundry list of properties that you'd like it to have, which is why it's a separate problem on its own that people have studied a lot, aside of multi-party computation. For example, just a small property is that MPC typically requires that all entities come together, they're online during the entire computation, and then they collectively learn the outputs. This is absolutely not feasible in a voting system. You want to be able to cast your vote and go away, right? And so that's a different property that you want out of the voting system. And then you want things like deniability and those kinds of things which are not automatically part of an MPC framework. So voting has been studied a lot. MPC is an umbrella term for this, but normally we use it in other contexts.
Okay. Thanks to our panelists and the audience, and I think we are finished now. Thanks all of you. I think there will be some felicitation.
Thank you all for joining this informative session. Now I would like to request Dr. Sridhar Shukla to come on the stage to felicitate our panelists. We thank Professor Shweta Agrawal, Dr. Nishanth Chandran, and Professor Chaya Ganesh. And we also thank our moderator, Professor Manoj.